Hi everyone, my name is Ludovic Peignard. I'm an exploration geophysicist, an associate teacher in IFP school, and the creator and developer of Earthquake, a piece of software dedicated to quick looks in geoscience. Today, I'm going to introduce you marine CSEM, Controlled Source Electromagnetics, also called seabed logging. My goal today is to explain simply on what relies mCSEM. That is quite a challenge, but the idea is to give you some hints to put you on track to subsequently reconstruct on your own the demonstration of physical mechanisms at stake. First, we must address the question, why EM techniques interest the E&P sector? And the answer lies just on those two graphs you see on the slide. On the top, it shows the effect of a change of gas saturation in the pore fluid of a 50 porous sandstone on both the acoustic wave velocity and the electric resistivity. And implicitly, that is a way to compare seismic and electromagnetics methods. And we may observe two curves. The green curve exhibits effect of a gas on compressional wave velocity, while the red one shows the effect of gas on the electric resistivity. And you can see that the largest effect on acoustic velocity occurs for very few percent of gas accumulation. But on the contrary, a disconnected bubble has just a little effect on electric resistivity, which does not increase significantly until 70 to 80%. That means we could fairly expect to see EM methods to succeed where seismic could just fail. The chart below shows materials which are part of E&P investigation and are distributed over a massive range of order of magnitude for the resistivity. And electric resistivity variations in sediments are controlled by porosity, permeability, geometry, and of course, fluid. So, as a good approximation, the industry often takes 0.3 for the seawater, 1.5 meter for sediments saturated with brine, and up to 100 meter for hydrocarbon-bearing reservoir. That is almost 2 orders of magnitude between sediments containing brine and those containing hydrocarbon. Here, this is a slide to describe a typical acquisition scheme and different kinds of diffusing waves observed with the mCSEM acquisition. On the top image, you could see electric and magnetic field receivers are laid just on the seafloor, and they record a time series measurement of the fields, in particular those which are emitted by the transmitter, by the source, which is a horizontal electric dipole. And it is stored by a vessel, generally about 30 meters above the seafloor. And the maximum range of acquisition, I mean the offset between the receivers and the source, is about 10 kilometers. So the CSEM signal transmitted by the source involves both vertical and horizontal current flows in the subsurface, which could be eventually interrupted by the hydrocarbon-bearing reservoirs. And the tremendous benefit of that EM acquisition layout is that it could provide sensitivity to this geological feature, even when they are quite thin, but with some physical limitations, of course. On the image below, you could see schematically what is typically retrieved for each receiver. It's actually a graph showing the amplitude of the field versus the source receiver offset. And you may identify 3 different zones on that graph. For near offset, direct waves dominate the recorded signal. They are marked in yellow in the 2 images. For far offset, you have airwaves refracted at the air-water interface, which dominate the overall recorded signal, since they are poorly attenuated when traveling in the air. And in between, you could eventually observe, for mid-offset, refracted waves by the hydrocarbon-bearing reservoir, which dominates both the air wave and the direct wave, which are now too attenuated by a phenomenon we shall define right away. This is the inductive effect, and first of all we have to define it. When a target is more conductive than the surrounding formations, inductive current lines induced by the EM wave draw a circle restrained to the conductive target. That leads to the creation of a magnetic dipole of which the orientation depends on the target geometry. That is what we call inductive effects, on what rely many EM methods which are time variant, including marine CSEM. And the sketch you could see on that slide illustrates that phenomenon, which is actually fairly explained by the Maxwell's equations. And we could consider the Maxwell's equation as our starting point to get deeper into the explanation of that inductive effect. At that point, I suppose you already have some knowledge about mathematical tools. I mean gradient, divergence, curl, Green-Ostrogradski theorem, Stokes theorem. A mini glossary has been added just to be clear about notification. And if you are not familiar with that, no worries, relevant references at the end of that course shall be passed to you. But first, a bit of history. Clerk Maxwell was a Scottish physicist, and with the help of Faraday, he developed the notion of EM planar wave with an electric field orthogonal to the magnetic field. Maxwell theory is based on 4 equations. The Gauss equations, which give you indications about the field lines geometry, and 2 other equations, the Faraday equation and the Ampere-Maxwell equation, to give you the explanation about how time and space are linked regarding electric and magnetic field. At first, no source in our volume of interest. We consider they are sufficiently far away in that version of the Maxwell's equation. And then the power of that is that the gathering of all these equations enables you to define the electromagnetic states everywhere at all times. Then you have here on that slide the conservation of the charge, which brings the divergence of the current flow equal to 0. It comes first from the divergence of the Maxwell-Ampere equation, with the fact that the variation in time of the electric charge density is equal, approximated to be 0. Because a free charge gets bounded very fast with subsurface materials we are used to meet with exploration and production sector. If we handle the Maxwell's equations and play with mathematical operators, taking the curl of the time variant equation, linking time and space, we end up with such an equation on the top of the slide. And the delta symbol refers to the Laplacian operator. Then, if k squared is defined as follows, we get the so-called Helmholtz equation, and k could be now called the wave number. And if we deal with geological matters and low frequencies below 10 Hz, we could simplify that equation of k, that expression of k. And back in time, we could recognize the so-called diffusion equation, also called the heat equation. Then k has a real and imaginary part, and that brings, at the end, an attenuation term. And we used to define the skin depth, commonly written delta, to quantify the amplitude loss of the diffusing wave. The more the conductivity and the frequency are high, and the more the signal gets attenuated, as shown on the sketch below on the slide. And if the wave travels of a distance equal to delta, amplitude loss reaches 67%. A similar effect could be observed on the phase, since phase velocity shall now depend on the frequency and the conductivity. Here we start from the Maxwell, the Gauss theorem, and the Stokes theorem. And we take an hypothesis. Two media are taken with different EM properties. Indices 1 and 2, unquoted physical quantities refer respectively to medium 1 and medium 2. Plus, if we use the Ohm's law, it brings that a wave passing from a medium with a certain conductivity to a medium with a different conductivity shall imply a step on the electric field. This is what we call the galvanic effect. But now we could ask the question, what shall favor vertical instead of horizontal currents to get that phenomenon at two layers interface? And that is exactly what is explained by the point 2. So point 2, if you use the boundary conditions and use of Maxwell's equations, it lets us demonstrate the Snell-Descartes law for EM waves. The subscript letters I, R, and T refer respectively to incident, reflected, and transmitted. But I'm pretty sure, since most of you geoscientists, you are very familiar with that expression regarding seismic. And like with seismic, you can reach a critical angle in some specific condition. For instance, if you go from a low resistivity medium to a high resistivity medium, involving normal current to flow. However, you shall understand that normal electric field component could be obtained with a specific acquisition layout, bringing what we call the TM mode, the transverse magnetic mode, opposed to the TE mode, the transverse electric mode, where no normal component of the E field could be observed. So please refer at the essential readings at the end of this presentation for more detail, more explanation, more references. As a resume, with an EM wave diffusing in the sediments, you could expect a positive anomaly on the normal component of the electric field and a horizontal guided wave when a highly resistive layer, like a hydrocarbon-bearing reservoir, is met, even if it's quite thin. Then, we need to show how behaves the E and H fields, the electric and magnetic fields, when we are dealing with a source in the area of interest that corresponds to our case with our typical horizontal electric dipole with mCSEM. Maxwell's equations are then slightly modified with the adjunction of current density of the source. Then we need a mathematical trick to solve such a system of equations. We use what we call the vector potential to solve that problem, with the assumption the H field is derived from a purely rotating field, the so-called vector potential A. That subsequently enables us to get back to the so-called Helmholtz equation using the vector potential. And we know how to solve it. And that brings a decay of the electric field varying like the inverse of the cubic offset, with IL, the moment of the dipole, I being the intensity of the current flowing in the source, and L, the distance between the two electrodes. And here now is a resume of different phenomena we have at stake. The geometric, we just saw it on the previous slide. The galvanic, it's increased by the contrast of conductivity and occurrence of normal currents, normal electric currents at the interface between two media. And people dealing with DC methods are used to those two effects. Then inductive effect, responsible for amplitude decay and phase delay function of the frequency and the conductivity. And I truly think that noises could be considered as well as phenomena to take into account, giving their importance. They are of different origin. You have the magnetotellurics, and at our frequency of interest, they all come from the interference between the ionosphere and the sun plasmas, the water motions. More you deep and more it's quiet. You are not sensitive to the swell noise anymore when you are in deep waters. Electronic amplifier noise. Recorders, they just are electronic devices, so naturally you have a noise threshold. And then human activities. You have, for instance, catalytic protections, power lines. We can add that, like for seismic, stacking helps to increase the signal to noise ratio. And quickly, just a piece of advice, giving multiplicity of phenomena at stake during mCSEM acquisition, so geometric, galvanic, inductive, plus the noises. Every mCSEM project requires a feasibility study to evaluate the electromagnetic response and the most likely subsurface resistivity distribution in the subsurface, giving an indication if the targeted hydrocarbon bearing reservoir could be detected or not. At least a 1D model must be run since it's fast and provides a sensitivity analysis. And we are now getting closer to the conclusion of that lecture, but we are also getting back to a slide of introduction with obviously more knowledge at your disposal now, and you could more easily understand predominance of different waves on the graph is the result of interactions between geometric, inductive, and galvanic effects. But what we did not cover today, nothing's perfect, and we did not cover many things actually. Historical point of view of a method, and I think it's still interesting when you are dealing with sciences, and TMT modes. The explanations were not sufficient to define them properly and to associate them to inline or broadside acquisition. Source signal signature, usually it's meticulously set up during the feasibility survey. And empirical study, we did not show any example, but I am with the first break publications and different references, you can find a lot of different examples. Recent developments, we only focused on the typical way to acquire CSEM, but research programs are on their way, and involving new techniques like, for instance, torque streamers, and like the use of transient domain to use that in shallow waters. I could leave you now a bit disappointed, but next slide intends to show where you could find some pertinent answers to the remaining questions. So this is acknowledgements and essential readings. It goes from magnetotellurics to enhancement of the mCSEM to enable use in shallow waters, and made that a long list, but you need to know more to master that technique, marine CSEM. I shall just focus on two different readings, the one which are quoted with bold fonts. First, the article of Constable. This is really relevant, pertinent synthesis of the techniques. It's one of the best reading you may have to get in synthesis of the method. Most of the drawings coming from that presentation are taken from that article. Then the one I wrote with the IFP and 3 other colleagues, we adopted an ebook format, so and it's 100% free and available at URL quoted on the slide, and it develops different EM methods used by geoscientists, and marine CSEM is one of them. That is all for today, and thank you for your attention. You can like and share this video, and for more e-lectures, take a look at the e-lecture playlist.